Hello, my friends. We are going to solve just a few real final exam questions that came up in the general chemistry course, and they pertain to entropy. There's different ways to define it, but it's a measure of how our energy is kind of dispersed or spread out. It's also a measure of how ordered our matter is in one way to look at it. So the more order it is, the less possible arrangements that we can make with that material. If we can make more arrangements, we have a more disorderly arrangement, then we can arrange them in different ways, then we have higher entropy. So the first one, couple questions are multiple choice. And this is the first one. Which of the following processes show a decrease in entropy? We're going to start from the bottom and work our way up. So ice cream melts. So if we think of ice cream as a solid, it's kind of stuck together, right? It's not moving around. The molecules are not moving around much at all. They're vibrating and whatnot, but there isn't too many different arrangements that they can make. But when it melts, we have the liquid. These molecules, the ice cream molecules, can move around and roll around each other. So we have more possible arrangements. We have more disorder of these molecules. They're more kind of spread out amongst themselves compared to being localized in certain spots for the molecules in the solid. So that means we have an increase in entropy. So when we're going from a liquid to a gas, like in water, we have more possible arrangements to put these molecules in a gas because they can go anywhere in the container. But as a liquid, they're stuck to each other. They are rolling around each other. So there are more arrangements possible than when they're stuck as solids. But when they become a gas, they can kind of fly all over the place and disperse themselves even more. So we have higher entropy as a gas. Here we have a solid going to another solid and a gas. Again, we have an increase in entropy because we're creating a gas. So the last one has to be A, and we're going from two gases to a gas, but we're decreasing the number of moles of gas. So we have on the left-hand side 3, on the right-hand side 2. If we add these numbers up, 2 and like there's a 1 here. So we're reducing the number of molecules in the container. That means there's less possible arrangements to have these molecules compared to 3. We have a lot more molecules in the container than for reactants than we do with products. Since we have less molecules as the products, we have less arrangements possible, less disorder. If you're okay with that word, some profs aren't. So it'd be a decrease in entropy. Okay, next one here, number 2. The entropy change when a liquid freezes may be represented as, so when a liquid freezes, it's in this liquid state. Now the molecules are bonded together loosely. They can roll around each other. They are moving. But when it becomes a solid, so it's going to freeze into a solid, our molecules are stuck in particular arrangements. So they're significantly more ordered compared to when they're in a liquid, and there's less different ways to arrange the liquid as a solid because they're sort of stuck in this it could be in a crystal form or an amorphous form or that sort of thing. So we have a decrease in entropy. So entropy, which is S, decreases. That means the change in entropy, which is entropy final minus entropy initial, this decreases. So the final entropy has to be less than the initial entropy. This is a smaller number. This is a bigger number. So this change in entropy has to be negative, has to be less than 0. This one right here. And enthalpy has to do not with entropy. Right? It's the heat transferred at constant pressure, usually in chemistry, is what we care about. Okay, a couple questions for short answers. Is the change in entropy for the following processes positive or negative, and why? And this is our first process. We have C4H8. It's a gas going to another gas, C2H4. And we're increasing the number of molecules. So if we think of our reactants, C4H8, let's say we have 3 of them. Say we have 3 C4H8 molecules. Well, for every 1 molecule of C4H8, we produce 2 molecules of C2H4. So if we have 3 molecules of C4H8, we're going to have 6 molecules of C2H4. So there'll be 1, 2, 3, 4, 5, 6. We have more possible arrangements of molecules with 6 ways to arrange molecules than with 3. These 6 can be dispersed everywhere, where 3 we don't have as many arrangements compared to that. We have an increase in entropy, so we'd expect delta S to be greater than 0. Next one here, C4H8 going to C4H8. So it's the same substance going to the same substance. So it's not changing substances. We're not doing a chemical reaction. We're still going from a gas to a gas. The temperature is the same, but we're decreasing the pressure under constant temperature. So how can we decrease the pressure? Well, there's not too many ways to do it, right? If we think of a piston here, and we have our C4H8. I'm sorry if this is small. C4H8, say there's 3 of them here. How do we decrease the pressure? Well, we can raise this piston up. We can increase the volume. So we just have a bigger volume. And since these 3 molecules have a bigger volume to go in, there's less collisions against the piston per time compared to when it's smaller. If there's less collisions against the piston, then the pressure is lower, so we've decreased the pressure. So by decreasing the pressure, we've increased the volume, increased the space in which they can roam around in. So that's kind of dispersed this mass. There's more possible arrangements that we can have 3 molecules in a bigger space compared to a smaller space. So there's less disorder here. So therefore, we have an increase in entropy as well. And lastly, same substance, C4H8, going to the same substance, C4H8. It's from a gas to a gas. The temperature is now going up. So we're just making it hotter. And it's going to be under the same pressure. So how do we do that? Well, we can't just have a closed flask, actually, and heat it up, because these would start moving faster. We'd have more collisions. They'd collide against the edge of the container at a faster rate, which would increase the pressure. So the only way to do that would be to increase the volume. So now we have a larger volume to move around in. Same scenario here. We have the change in entropy is greater than 0. Yes. Hope that won't trip you up. And this one always trips people up, but hopefully it won't trip you up. For the reaction of A2 colorless and B2 gray. So this looks like this is A2. This is A2 here. This one's A2. And this is B2. What's the balanced equation and sign of delta S? So let's see what's going here. We have 2 A2s. And we have 1, 2, 3, 4, 6 B2s going to, now this is a AB3. It looks like AB3 molecule. They're all AB3s. Okay, 1, 2, 3, 4, 1, 2, 3, 4, 2, 4, 6, 8, 10, 12. 1. Okay, so it's all balanced. And how many are there? 1, 2, 3. There's 4. There's 4 of these. Okay, so this is fine, and it's balanced, but it's not in reduced form. Everything's divisible by 2. So I'm just going to divide everything by 2 to get it in lowest form. And this is our balanced equation in all its glory. And what about the sign of delta S? Well, if we think about how many possible arrangements we can have in space, here we have 1, 2, 3, 4, 5, 6, 7, 8 molecules bouncing around versus 4 molecules bouncing around. We have more possible arrangements with the 8 bouncing around. Think of these 4. We hear for each one of these molecules, these product molecules, it's like we have 4 atoms kind of stuck together. So we've ordered 4 atoms in every clump of molecule, but we've only ordered 2 molecules at a time in the reactant. So we have more order on the right-hand side and less arrangements within this container that these 4 molecules can make than this one. So the change in entropy has to be less than 0. Okay, another final exam question that came up that I was able to find is this change in entropy of the surroundings. Is the change in entropy of the surroundings, that's what SURR means, for the following processes positive or negative y? If you see this, delta S with no subscript, that just means for the system. So that's the change in entropy for the system. Yeah, if it's like even enthalpy, change in enthalpy, if there's no subscript, that's for the system as well. If it's for the surroundings or something else, then we'll indicate that, so the surroundings. Okay, so is the change in entropy surroundings for the following process should be processed as positive or negative. And why? An endothermic reaction. So an endothermic reaction has a delta H that is greater than zero. Wrong way. That is greater than zero. That means it's positive, which means if we have the system here and the surroundings here, positive means, so under constant pressure, then Q would be greater than zero. So we have heat transfer to the system. So we have heat transfer occurring from the surroundings to the system. The surroundings is losing energy as heat, and this energy as heat has to do with the kinetic energy, the motion of the molecules in the surroundings. If they're giving off, transferring some of that kinetic motion into the system, because that's what heat transfer is, then we have less kinetic energy of the molecules in the surroundings. They're not moving as fast, they're not bouncing as vigorously against each other, they're slowing down. Potentially, yeah, they're slowing down because they're transferring to the system. So we have this negative delta S is going to be, we expect it to be less than zero because they're slowing down, less possible arrangements in space when they're not moving as fast. There is a quantum mechanical explanation, which we shouldn't get into for this video. The condensation of water. So condensation is when we go from a gas to a liquid. So think about how many orientations we can have for the molecules as a gas. They can go anywhere in the container, but they're stuck together in some way in the water. They can roll around each other and they are free to move somewhat, but not as free to move around compared to a gas. So we have less arrangements and a decrease in entropy for the condensation of water. Alrighty, last final exam question. How can the second law of thermodynamics be valid if entropy decreases when water spontaneously freezes at 0 degrees Celsius? And this comes up all the time, a short answer question. The second law of thermodynamics says that the change in entropy of the universe for a real process is always greater than 0. Here we have a process, we have water freezing. So we have water, liquid water, right? Molecules are moving around. We're freezing it at 0 degrees Celsius. And now these water molecules are stuck to each other. So we have this decrease in entropy. Well, how can the change in entropy of the universe increase when we have the system decreasing? Well, the answer is that we need to look at the surroundings as well. This change in entropy of the universe in thermodynamics is usually broken up into the surroundings and the system. So the change in entropy of the universe equals the change in entropy of the surroundings plus the change in entropy of the system. And these two combined have to be greater than 0. So if the change in entropy of the system is less than 0, then the change in entropy of the surroundings has to be greater than the change in entropy of the system. So if we solve for the change in entropy of the surroundings, so if this is less than 0, then, well, we need the surroundings to be greater than the change in entropy of the system. So that's it. So it doesn't violate the second law because the change in entropy of the surroundings is positive and greater than the change in entropy of the system. Okay, everyone. Hope you enjoyed it. Thanks again for watching, and I'll see you in the next video. Cheers.